Okay. Uh, so I think we're good to start. So last time we just uh, gave some definitions about differential equation. What is a differential equation? It's an equation with derivatives of a function. So you have at least two variables. One we call it x, for example, and the other we call it y. And we're supposed to solve for y from this equation as a function of x. So the solution of this differential equation is actually a function. Okay, it's not a number. Um, we have different types of differential equations. Sometimes you may get uh, two or more functions in a equation with derivatives, and sometimes you get two or more independent variables in the equation. Okay. And then we have ordinary differential equation, which has only one independent variable. So you don't have partial derivatives. You just have ordinary derivatives. And then we also have partial differential equation, which involves partial derivatives. And that means in the equation, you have at least two independent variables, so that you have to specify the derivative with respect to which independent variable. All right. So those are called ordinary differential equation, ODE, and the partial differential equation, PDE. And as I just said, the solution of a differential equation is a function. Okay, we need to solve for the function from the differential equation. So when you plot the solution of the function, or you know of the differential equation, then it will give you a curve, right? You plot the graph of a function, which is the solution of the differential equation. Uh, it should give you a curve. So we call this a solution curve. So the graph of a solution phi of an ordinary differential equation is called the solution curve. So in this whole semester, we just talk about ordinary differential equations. We don't deal with partial differential equations. Okay. So the next thing is implicit solution. All right. You might have learned this or heard about it before. So it just means the solution of the differential equation is an implicit function. Okay, the function is defined in an equation with uh, variables where the function is not expressed explicitly in terms of the independent variable. Okay, so you got the function and the variable, or the dependent variable and the independent variables mixed together. All right. So that's called an implicit solution of the differential equation. So a relation g of x, y equal to 0. So you can see this relation. Okay, it doesn't have to be a function. It's just the equation with both x and y. So we suppose the x is the independent variable, y is the dependent variable. So ideally we want to write y as a function of x explicitly. So you have, for example, y equal to 2x plus 3. That's an explicit function. Or y equal to x squared plus 1. You know, those are explicit functions. But in this relation, g of x, y in general, x and y are mixed together, and y is not expressed explicitly as a function of x. So this is a general equation with x and y. So this relation is said to be an implicit solution of an ordinary differential equation on the interval I. So you don't have to worry about those, you know, interval, at this point if you're not familiar with it. Mathematically, we always do it regardlessly. That's why we have some wording like this. So provided that there exists at least one function phi that satisfies the relation as well as the differential equation on I. Okay, so that means y equal to phi of x. If we plug it into the relation, it should satisfy this relation. Okay, so in other words, we got an implicit solution. All right, but the solution is not expressed explicitly in terms of x. It's defined in this relation or equation. Okay. Does anybody have any questions, or if you can turn off your microphone? Hello, Kirsty, do you have any questions? I have to mute it. There's some noise, so I'm going to mute it. All right. Okay. So that's the definition. Like any other equations, you can have implicit solution or implicit function that satisfies the equation. Okay. Any questions? Okay. Okay. In many cases, when you try to solve a differential equation, you're gonna get the an arbitrary constant. Like when you integrate. Remember, when you do the integration, you find the antiderivative, and the antiderivative always involves an arbitrary constant c. If you still remember, kind one. When you integrate the function, you always end up with arbitrary constant c. So a solution containing an arbitrary constant represents a set of solutions, which we call g of x, y, z equal to 0. And this set of solutions is called the one parameter family of solutions. Okay. So when you try to solve a differential equation, you get the family of solutions instead of just the one, because there is an arbitrary constant c in the solution, as we can see from the examples. Okay, so let's just see one example. The one parameter family y equals c x minus x times cosine x is a explicit solution of the linear first order differential equation xy prime minus y equal to x squared times sine x on the interval from negative infinity to positive infinity. Okay. So we are given a family of solutions, y equal to cx minus x times cosine x. It is a one parameter family of solutions because we got an arbitrary constant C in this solution that you can choose for any value. Okay, so it's not just the one solution, and it is a explicit solution because the function is written as y expressed in terms of x explicitly. All right, so that's an explicit solution, and this will be a solution of the linear first order differential equation. Okay, and this is a linear differential equation because all the y's and the y primes are linear. The exponent for each of those y and y prime, it's one. So that's a linear in y and y prime. And it is first order because the highest derivative is one, first derivative. So it's first order. Okay, remember we talk about these things on Wednesday. And this solution is valid for all values for x. That's what it means. Values into from negative infinity to positive infinity. It means it works for all the values for x. Okay, so let's just double check to make sure this function y equal to cx minus x times cosine x is indeed a solution of this differential equation, xy prime minus y equals x squared times sine x. So as we did before, what do? We just find the derivative of the function and then plug into the differential equation and see if the equation holds. All right. So the function is y equal to cx minus x cosine x. So we need to take the derivative of y. So that's y prime. And it has two terms. So you just take the derivative term by term. So we get a cx prime minus x times cosine x prime. And the first term is simple. The derivative of x is just one, so you got a c times one. C is a arbitrary constant, remember? So that is a constant. All right, so you can take out from the derivative. The second term of x times cosine x, again, this is a product of two functions, x and cosine x. So we have to use the product rule. Remember, what rule you use depends on the problem. So in this case, we have to use the product rule. So the product rule says the derivative of a product of two functions is equal to the derivative of the first function times the second function plus this first function times the derivative of the second function. Okay, so that's x prime times cosine x plus x times cosine x prime. Okay, remember prime means the derivative. So some people always messed up with those notations. Okay. Keep in mind, prime means the derivative. Okay. So then the first term c times 1 is just c. And the second term, we got x prime. The derivative of x is just 1. And the cosine x prime, that's the derivative of cosine x, which is negative sine x. Okay. So we got, c minus 1 times cosine x plus x times negative sine x inside the parentheses. If we simplify the second part, 1 times cosine x, just cosine x, and the x times negative sine x is just negative x sine x. Okay, we got negative here. And then you distribute the negative sign to the second part. You got the c minus cosine x plus x sine x. Okay. So now we are ready to plug in y prime into the differential equation and see if the equation holds. So on the left side of the equation, we got xy prime minus y. And we already found the y prime in here. So just plug it in. So what we get is x times c minus cosine x plus x times sine x. That's the first term on the left of the equation, minus y. And y is cx minus x cosine x. Okay, just plug in. And then we distribute x in the first part of the left-hand side. So we got a cx minus x cosine x plus x squared sine x. Okay, remember x times x squared, and we always put the constant in front. Okay, and in the second term, we got negative sign to distribute. So that becomes negative cx plus x cosine x. Now you can see cx and negative cx cancel. Negative x cosine x and the positive x cosine x cancel. So what is left is just x squared sine x. And if you compare this result with the right-hand side of the equation, they are exactly the same. So what it says is this, one parameter family of explicit solution does satisfy the differential equation. Okay, the left side and the right-hand side match the equation or the differential equation when we plug in the function into the differential equation. So that means the function is a solution to the differential equation. All right. So we have done that part. So as I said before, C is an arbitrary constant that you can choose arbitrarily. You can choose for any value. For example, if you choose C equal to 0, then you just get one solution. So if we plug in 0 for C in here, 0 times x just gets 0. So it becomes y equal to negative x cosine x. So that's one solution. Okay. You don't have any arbitrary constant now because you already choose it to be 0, C equal to 0. So you just get the one solution. That's called the particular solution. So if you choose another value for C, if you choose C equal to 1, for example, then you get the y equal to x minus x cosine x. That's another particular solution. Anytime when you choose a specific value for C, you get the one solution. We call it the particular solution. All right. Any questions about this example? So the particular solution is just one solution from the general solution. I have no question. Let's just continue to another example. So we just discussed one example with one parameter of solution. Sometimes we may have two parameters in the solution, and that's still a family of solutions. So in this example, we have a two parameter family of solution, y equals c1 e to the x plus c2 times x times e to the x. So there are two parameters, c1, c2. There are arbitrary constants. Again, you can choose freely. And it is again a explicit solution because it is written as y equal to in terms of x. So it's explicit. And this solution is a solution of the linear second order differential equation y double prime. So the second derivative y minus 2y prime plus y equal to 0. So we got the second order differential equation here because there has derivative is second derivative, so that's second order. Remember, and it is still linear because all the terms with derivatives y and y itself are linear. The exponent for all those terms of y double prime, y prime, and y is 1, in other words. Okay, so it's a linear differential equation. So let's just double check to make sure this solution is indeed a solution to the differential equation. So this time we need to, find the first derivative y prime and the second derivative y double prime. All right, and then plug into the equation and see if the equation holds. So let's start from the first derivative y prime. Okay, so you have to find the y prime to get y double prime. All right. So I think we did a similar example before, but let's just refresh your memory. On how to find the derivative of this function. So we got c1 e to the x plus c2x times e to the x as y, and we want to find the derivative of this function. So you can take the derivative term by term. So we get c1 e to the x prime plus c2x e to the x prime. Okay, the first term is very simple because c1 is constant. The e to the x derivative is e to the x itself. The second term involves the product of two functions again. One is x and the other is e to the x. So we have to use the product rule again. So the second term becomes 2 times x prime times e to the x plus x times e x prime, the product rule. And x prime is just 1, the derivative of x is just 1. And derivative of e to the x is just e to the x itself. Okay, so this is relatively simple. All right, so that just plug in those and simplify a little bit. 1 times e to the x is just e to the x in the second part. X times e to the x. Okay, so we got the c1 e to the x plus c2 times e to the x plus x e to the x. So if you distribute the c2 in the second part, we got c1 e to the x plus c2 e to the x plus c2 x times e to the x. So that's y prime. And the first derivative of the function. And then we need to find the second derivative of the function, y double prime. So what it do is just take the derivative of the derivative. So we already found the derivative of the function. So we just need to take the derivative of this function one more time. So we're going to c1 e to the x plus c2 e to the x plus c2x e to the x prime. All right. Now, again, you can split this derivative into 2 parts or 3 if you want. So if you, combine the first and this third term and the split the other term, the second term, then we get a c2 e to the x prime plus c1 ex plus c2 ex e to the x prime. Okay. And the way I write in this way is because we already found the derivative of this c1 e to the x plus c2x e to the x. Remember when we did the first derivative? Okay. So then we just use the result we already got. We don't have to do it over and over again. Okay. That's why I just rewrite the steps like this. The first term is c2 e to the x prime. Again, c2 is a constant, and the derivative of e to the x is just e to the x. So that gives us c2 e to the x. And the second part is C1 e to the x plus C2x ex prime, as we already did in the first step. Is C1 e to the x plus C2 e to the x plus C2 x e to the x. Okay. So just plug in the result. Now you can combine like terms. We got a C2 e to the x appearing twice in the result, so we can combine them to get 2 times C2 e to the x. And just keep other terms as they are. So that becomes C1 e to the x plus 2, C2 e to the x plus C2x e to the x. So that's the second derivative of y. And then we can combine, we can plug in y double prime and y prime into the equation and see if the equation holds. Okay, so y double prime. Okay, we got in here C1 e to the x plus 2 C2 e to the x plus C2x e to the x. All right. Minus 2 times y prime. So y prime is C1 e to the x plus C2 e to the x plus C2x e to the x. All right. And the plus y. That's C1 ex e to the x plus C2 x e to the x. Okay, plug in here. And then just simplify the whole thing and see what happens. Okay. So in the second part, you can distribute -2 and to everything, and we get a -2 C1 e to the x minus 2 times C2 e to the x minus 2 C2 x e to the x plus C1 e to the x plus C2 x e to the x. I don't know why I wrote 2 plus signs in here. I don't need 2 plus signs. Okay. So it's a typo. So now let's just see what happens. So we got a C1 e to the x in here, and then we got -2 C1 e to the x, and then we got another C1 e to the x. So, those 3 terms cancel. See? For the C2 e to the x, we got a 2 C2 e to the x, and -2 C2 e to the x. They cancel completely. Okay. So we cancel those 5 terms. 1, 2, 3, 4, 5. And then we are left with 3 more terms. C2x e to the x minus 2 C2x e to the x plus C2x e to the x. So again, they cancel completely. So everything is canceled. So we got 0. So that's exactly what the equation says. So that means the function does satisfy the differential equation. So we have verified that the 2-parameter family of function y equal to C1 e to the x plus C2 x e to the x is indeed an explicit solution of the linear second-order differential equation. All right. So then, just like before, you can choose any value for C1, C2 to get a particular solution. For example, if you choose C1 equal to 0 and C2 equal to 5, then we get a solution y equal to 0 times e to the x plus 5 times x e to the x, which is just 5x e to the x. So that's a particular solution. You can choose any other values for C1, C2, or arbitrarily to get another particular solution. So that's a family of solutions with 2 parameters. All right. Any questions about this example? I think it's straightforward. You just need to remember how to take the derivatives. Okay. If no question, then we just go to the next page. Okay. So the last thing is called the system of ordinary differential equations. So what is the system of ordinary differential equations? Just like any other equations, a system, that means you have 2 or more equations in the problem. Okay, so A system of ordinary differential equation is two or more equations involving the derivatives of two or more unknown functions of a single independent variable. Okay, so we only have one independent variable, but we have two or more functions to solve. Okay. So it involves two or more equations. So for example, the following is a system of ordinary differential equations. The first equation is dx over dt equal to f of t xy. And the second equation is dy over dt equals g of t xy. So you can see there are two functions or two independent variables, x and y, that we need to solve from this system. And there's only one independent variable, t, we call it t. Okay. So those equations involve all of the variables t, x, and y. You know, you can see f and the g are both functions of t, x, and y. But there's only one independent variable t and two dependent variables x and y that we need to solve from this system. All right. So these are some basic definitions about differential equations. We have not done anything on how to solve differential equations, which we will do it in the whole semester, step by step in different types of differential equations. But we have to learn these basic concepts before we even start to solve the equations. Any questions about this section? So we are done with the first section. Okay, if not, then we're going to start 1.2 Wednesday next time, next week. I think there's no class on next Monday. It's a holiday. So these are some practice problems that, for this section that you can work on them. It's not homework. These are not homework, just practice. You can practice by yourself to to do it by yourself at home. You don't have to submit them. Just for you to learn. All right, they're not assignments. And you got the book from ebook from online, so you can find these problems from the ebook easily. Any questions? Anything you want to discuss with me? Any? If not, then I'm gonna stop in here, and let me just stop the recording.